Welcome back. I've got good news and more good news. In this video, we're going to finish up prisms, and we're also going to work to simplify and dominate total prismatic effect. In this video section, we're going to go over correcting vertical imbalance, image jump, and then finish with total prismatic effect. So let's get in the text and talk about correcting vertical imbalance. We talked about vertical imbalance and how to calculate that in the last video, but now we're going to kind of take this next step to clinical and say, okay, now we've got a patient that has vertical imbalance. What are some things that we can do to try to help minimize that vertical imbalance the patient may have, right? And the first one that comes to mind is what? Yeah, it's going to be slab off prism, right? So one key thing here about slab off prism I want you guys to highlight here is that you change the shape of the more minus lens so that it ends up having more base up prism, right? So to me that was always kind of confusing whenever I was a student until I heard someone mention BUM, right? So base up to the more minus lens, right? And that just, ever since that day, like it's just like every time I think of slab off prism, I think BUM every single time, right? And so I would suggest writing out to the side, base up, more minus BUMM, and I think that'll help you be able to dominate any kind of question about slab off prism as you move forward, right? So continuing on, whenever you talk about other clinical ways to try to minimize vertical imbalance, right, that you guys may come across whether you're studying or whenever you're in clinic, right? One of the things we always think about is what? Contact lenses, right? So that's going to be listed here in our list, right? So contact lenses are a good way to minimize vertical imbalance. Another one is going to be using dissimilar segment, right? So we have different seg heights and different seg styles, right? Now, of course, that's not going to be as cosmetically pleasing to our patients, right? But it is definitely an answer that could come up, right? And the last one's going to be Fresnel prisms, right? Or our press-on prisms that we would put on a patient's eye, our patient's glasses. You don't want to put it on their eye, but you want to put it on their glasses, right? To try and help minimize vertical imbalance. So let's talk about image jump. You guys remember we wrote image jump down as one of the 4 ways that we could talk about Prentice's rule but using a different name? What were the 2 things we wrote out to the side? Yeah, the only 2 things you need to know for image jump is going to be the add type, right, and the add power, right? So add type, add power. Now, what is image jump, right? Image jump is just simply how does the image jump or move as you go right across this bifocal line, right? So as you go right across the bifocal line, it doesn't take into account the distance prescription. It doesn't take into account where the image is going to be located at because of distance prescription. All it's talking about is as a patient moves their eyes down, right, and they go across the bifocal line, how much is that image going to move? That's image jump. All right, so you guys want to highlight that in the text. So first line there is image jump refers to the sudden displacement of an image at the bifocal line. Now let's go through example 5.18. Find the image jump in bifocals given a prescription +2 -125 axis 180. The add power is a +2. In this case, the segment is a flat top 28 bifocal. The seg drop is 4. So take a second, pause the video, and you can work out the problem. So let's work this solution together. So whenever we're doing image jump, remember all we're going to be doing is simply Prentice's rule, right? And remember all we care about is the add power and the segment type. Now why do we care about the segment type? Because this distance that we're going to use in our Prentice's rule, right, is going to be the distance, right, from the top of the bifocal to the optical center of that bifocal, right? And for a flat top 28 bifocal, what was that number again? Yeah, that was going to be 0.5 centimeters, right? Or 5 millimeters, right? Now I wrote down 0.5 centimeters because that's what we're going to use. Every time you do an image jump problem, right, in a flat top 28 bifocal, you're going to use 0.5 centimeters as your distance from the optical center, right? That's why we had that number memorized. You guys remember the other 2 numbers that we memorized? Yeah, executive bifocal, right, which was going to be a 0, right? And then also is going to be the round seg bifocal, right, which is going to be the radius. So if it was like a round seg 24, right, that would be 12 millimeters. And what we would do is we would use 1.2 centimeters here for our distance, right? Now look in the question, right? In the example, it also gives you the distance prescription. It gives you the seg drop. Those are just distractors. You don't care about those at all, but they're going to be there to try and help, to try and distract you, try and make you think that you need to use the distance prescription when doing image jump. You don't. All you need, add power and seg type, right? Seg type is going to give you this distance from the optical center to the top of the bifocal, your 0.5 centimeters. And then your add power of 2 is going to give you the power you're going to get, power you're going to use. And for your image jump, right, we're going to get an answer of 1 diopter for this problem. Now, the second question that could come up is what base direction are you going to get, right? Now, for all image jump problems, right, where you have a plus add power, right, which is going to be typically the case, right, you're going to have what kind of prism that's going to be induced with image jump? Is it going to be base up or base down prism? Yeah, so if we look at our picture, we draw out our little triangle, right? Okay, what's going to happen is we're always going to be, as we go across the bifocal line, we're always going to be above center, right, in a plus lens, which means we're always going to have base down prism, right, with image jump if we have a plus add power. All right, guys, let's keep on going. We'll finish up with total prismatic effect. So let's talk about total prismatic effect. So the first thing we want to look at is we're going to talk about total prismatic effect. Remember, we talked about it. We said it's going to be one eye, right? One eye. So I've got a picture drawn up here that's going to help us out with example 5.19. So example 5.19 says, what is a total prismatic effect in the right eye when a patient looks down through a bifocal at a reading level of 15 millimeters below the major reference point, right? Sounds like a really complicated problem, right? Hopefully by the end of this, you're going to feel like, oh yeah, I can dominate this, right? So we're going to try and simplify this as best we can, explain it really well, and to the point where you guys are going to be able to dominate this and feel really confident about it as you're moving forward. So here's our picture, right? So we've got our patient's got a bifocal lens, right? They're going to be reading here 15 millimeters, right, below the major reference point. Okay, that's going to be their reading level. We also documented and noted where the near optical center is going to be located at. Now, this is a flat top 28 bifocal, so that'll be something that we'll use as we go forward. The other thing that we're going to need to know is we're going to need to know the vertical power of the distance prescription. So I went ahead and put that on a power cross, right? So now whenever we think of total prismatic effect, what are we talking about? We're talking about the fact that this patient, right, is reading here. Actually, let's draw it like this because they would actually still be in their bifocal. So they're going to be reading right here in their bifocal, right? So what we got to do is, okay, they're reading at this level. What kind of prism is induced, right? Now, if this was not a bifocal, right, this would be a simple Prentice's rule problem because it would just be a simple decentration. You would use 15 millimeters or 1.5 centimeters as your distance and the power in the vertical meridian. You do Prentice's rule and boom, there's your answer, right? But now we've got a bifocal that the patient's looking through, and so that makes things a little more complicated, right? Well, what we're going to do is we're going to treat this as two separate problems. We're going to treat it as like the distance lens. Think of it as the distance lens for one problem, and think of the add as just being a separate lens, right? They're kind of just sandwiched together. So we're going to separate them, do Prentice's rule for each, and then at the end, we're going to add the numbers together to get our final answer. So whenever you look in the text, if you guys want to highlight exactly what I just said, it's going to be that paragraph right above this example, right? The total prismatic effect from looking in a given location, you sum the prism induced from looking away from the segment optical center, the near portion, right? And the prism induced from looking away from the distance optical center, the distance prism, all right? So a couple things that we need to know. We know the distance from the optical center, the distance optical center, to where we're going to be reading at. That's going to be that 15 millimeters. So we've got that. We're good to go. We can figure out the distance portion as it is right now. But the near portion is a little more of a challenge, right? What we need to know to figure out the near portion is we need to know this distance right here. We need to know what is the distance from the near optical center to our reading level, right? What's the distance from the near optical center to our reading level? So to figure this out, we're going to have to remember a definition that we highlighted a few sections ago, and that was going to be seg drop. Right? What was seg drop, right? This is going to be the example where it's going to be the seg drop is what's going to unlock this example so we can dominate, right? So seg drop in our example was 4 millimeters. Well, what I want you guys to write out the side of seg drop is that's the major reference point to the top of the bifocal line, right? So we got 4 millimeters here for our seg drop, right? So that's from the major reference point to the top of our bifocal, right? That's going to be 4 millimeters, okay? So now we've gone from the major reference point to the top of the bifocal. What we need to know is from the near optical center to the reading level. Well, how are we going to get from the top of the bifocal to the near optical center. Flat top 28, right? What's that distance? We just used it in image jump. Yeah, it's going to be 5 millimeters, right? So it's 5 millimeters from the top of the bifocal segment to the near optical center. So if we take 15, let's do it right over here. If we take 15, right, which is our total distance, subtract out our seg drop, subtract out the distance from the top of the bifocal to our optical center, what we'll be left with is that distance from the near optical point, near optical center to our reading level, right, which is going to be 6 millimeters, right? And this is what we need to use to be able to calculate the prism that's going to be induced by the bifocal, right? Because that's this number right here, the distance from the near optical center to the reading level, 6 millimeters. So to say that one more time, right? Our total distance is 15 millimeters, right? So 15 millimeters, we go 4 millimeters to the top of the bifocal, that's our seg drop, another 5 millimeters to the near optical center. So this distance from the near optical center to the reading level is going to be 6 millimeters. To solve this problem for total prismatic effect, what we're going to do is we're going to do Prentice's rule twice, right? Once for the distance portion and then once for the near portion. So for the distance portion, we're going to use 1.5 centimeters times that 1 plus 1.5, which is going to be the power in the distance meridian, or the vertical meridian of the distance power. And we're going to get 2.25 Doppler's base up prism, right? Think of this is a plus lens, so think of it as two prisms base to base. We're looking below the optical center in a plus lens, so we're going to get base up induced prism. Now for the near portion, right, we're going to use 0.6, right? 0.6 centimeters, right? Our 6 millimeters here, right? We're going to use that and convert that to centimeters. Multiply that times the add power, which was plus 2 given to us in the problem, and we're going to get plus 1.2 diopters of base up prism. Okay, so we've got 2.25 diopters of base up prism from the distance prescription. We've got 1.2 diopters base up prism based solely on the add power prism. So to figure out our total prismatic effect, what we're going to do is we're going to add those two numbers together, right? So we take 2.25 and 1.2, and in the end, since we're adding them together and we are doing this over one eye, right, we're going to add them together and get 3.45 diopters of base up prism, right? So one key point to remember, we wrote this already, but remember this is one eye, right? And so if we take 2.25 diopters of base up prism and 1.2 diopters of base up prism, essentially optically, right, we can add those together whenever they're over one eye and get a total value of 3.45 diopters of base up prism when this patient looks 15 millimeters below the optical center, the distance optical center in their bifocal. So hopefully that made some sense. We'll go through this again in the live lecture. So go dominate the quiz and I'll see you on the next video.